to derive Biot and Savart law for an infinite wire with current. Let's say that I have a wire that has current I pointing upward, and then I take a point P at the distance D from the wire, and I ask myself what is the direction and the magnitude of the magnetic field at P. The magnetic field is, we will see, equals to mu 0, the permeability of vacuum, times I, the current, divided by 2 pi d. The direction of the magnetic field is obtained with the right-hand rule. So let's use the thumb taking the direction of the current, and the four fingers are curling around the direction of the wire. Therefore, on the right side of the wire, the magnetic field lines will be entering the page. At the point P, the magnetic field will be entering into the page. Now let's see the magnitude of the magnetic field. I start from Biot and Savart, dB equals mu 0 divided by 4 pi times the current I dl cross product r hat over r squared. And now I take an infinitesimal amount I dl of current on my wire. Let's say that this tiny arrow here is my IDL, which I like to place on the y-axis. And then I connect this tiny infinitesimal amount of current with the point P. That dotted line will be my distance r to the point P, and this small vector that I'm about to draw is my r hat, the unit vector r hat along the direction of the vector r. And then my wire infinitesimal IDL, let's say, because I am on the y-axis, is let's say along the y at the distance y from the origin. Let me call theta the angle at the point P. Therefore, the angle between the infinitesimal I dl and r hat is pi over 2 minus theta. And now I can work on Biot and Savart law. I have mu 0 divided by 4 pi times I. Instead of dl, I will write dy, and when I have to do the cross product with r hat, I need to include the angle sine of pi over 2 minus theta, and then I divide by r squared. And that I know that is in the direction, in this case, of the negative k into the page. If I want to find actually b, I will need to integrate on the left and on the right. So I will obtain that b, and let me now work in magnitude, is equal to, and then I have mu 0 over 4 pi, and then I can also bring the current outside of the integral, and then the integral of dy, and then sine of pi over 2 minus theta divided by r squared. And technically I will integrate all along the length of the wire. Let's start with a finite wire, and let's say that the wire goes from A to, on the bottom I will have negative A. So technically I will have to integrate between negative A and positive A. but I can just simply integrate between 0 and a and double the answer. So let's now work on the sine of pi over 2 minus theta. This is the cosine of theta, so I will rewrite, simplifying the 2, mu 0 times I divided by 2 pi integral between 0 and a of dy, then I have cosine theta, and I divide by r squared. Now in this integral, you see that you have y, theta, and r that in some way are all connected. I want to express the y and also r in terms of x. Actually, I called it d, so in terms of d, the distance, and in terms of theta. D is like a given. Theta is variable. So at the end I want to integrate in terms of theta only. Let me start by looking at the triangle that I'm going to highlight in yellow. This triangle has the hypotenuse equals to r, one leg vertical y, and one leg horizontal d. D is like a given. So I can write first of all that r can be rewritten as d divided by the cosine of theta. And then also y can be rewritten in terms of d and theta as d times the tangent of theta. But what I want in my integral is dy. Therefore, I'm going to derive dy is equal to d, and then I have 1 divided by cosine squared of theta. D, please don't get confused, d is the distance along the x-axis. Now let's substitute dy up here and r up there, obtaining that the magnetic field B is equal to mu 0 I divided by 2 pi integral between 0 and a of and then you have cosine theta. Then I'm substituting the differential dy with the distance d divided by cosine squared theta divided by the distance d squared over cosine squared theta, and here I also have d theta. I can cancel cosine squared. I can even cancel d, and I obtain mu 0 I divided by 2 pi d integral between 0 and a of cos theta d theta. Now the integral of cos theta is the sine theta, so I have that b is equal to mu 0 I divided by 2 pi d sine theta that I want to evaluate between 0 and a. And if I go back into that triangle with the little infinitesimal amount of I, d, l, the maximum that I, d, l can reach is the a. So I have this, my triangle, with one side that is a, another side that is d, and the hypotenuse, that is a squared plus d squared. Now when the maximum theta is with the sine of theta, that is equal to a divided by the square root of a squared plus d squared. Let me substitute here. I have that magnetic field B is equal to mu 0 I divided by 2 pi d as in distance times a over the square root of a squared plus d squared. And this is the magnetic field for a finite wire that has length 2 times a. But now let's imagine that my wire is infinitely long. So for the limit for a that is approaching infinity. So you will have a wire that is infinitely long above and below. And let's say that the current is pointing upward. When I take the limit of this ratio, that is equal to 1. So I will obtain that the magnetic field B for an infinite wire is mu 0 times I divided by 2 pi times the distance. Often this distance to the point P, instead of being called D, is called R. So often you will see that in this equation you have R, and that is Biot and Savart for a long wire.